Here are the solutions for the mock exam for applications of differential calculus. First problem. The following diagram shows the graphs of displacement, velocity, and acceleration of a moving object as functions of time t. Okay, so just be careful. This is the x-axis here, or the t-axis, and this is the y-axis. Okay, and there's three functions here, a, b, and c. And the first thing it says is to identify which functions, a, b, or c, are displacement, acceleration, and velocity. Okay, there's a few ways to do this. The most intuitive way to do it is remember that as you take the derivatives of a polynomial, it just gets less curvy, less curvy, less curvy. And so, for example, you start with like a cube, let's say, and then you have an x squared, and then you take another derivative, and it's a straight line. So just from that, you can already suspect that graph B is acceleration, graph A, which is the curviest, is displacement, and graph C, which is a parabola, is velocity. Okay? That's one way to do it. Okay? Another way to do it is you could pretend you're taking the derivative of each one of these, right? And this is kind of like the investigation we did for the properties of curves section. But like, for example, if you're going to take the derivative of graph A, you might like divide it into the negative gradient portions, like here. This would be a negative gradient. This would be a negative gradient. And then you'd have a positive gradient like here, right? So the derivative of this function, you would expect the red portions to yield below zero sections, like here and here, and you would expect the other parts to be above zero sections, like here, right? So you can see that graph C is possibly the gradient, or the derivative function of graph A, right? Because the signs of graph C correspond to the gradients of graph A. And same thing with graph B. If you were gonna say, okay, let's see where graph B is positive gradient, where it's negative gradient, you would say it's positive gradient here, and it's negative gradient here, and so that would correspond to a function where you would expect like positive values and negative values afterwards. So there's a correspondence there, right? So you can see that graph B is probably the derivative of graph C. The other way you might do it, and this is a third way, so like each one of these ways you could use to do the problem. Like for example, graph A, you could say, oh, all the places where graph A has a flat gradient, that would correspond to a derivative of 0. So the derivative function should have a 0 at every point that there is a stationary point for graph A. So you can see that graph C is indeed a derivative of graph A. And then the same thing with graph C. You could say, oh, graph C is a stationary point there, so it should correspond to a 0 point for its derivative, which is there. Okay, so those are three ways you could do it. You can use the positive sections and the negative sections of the gradient. You could use the stationary points that correspond to zeros of the derivative, or you could go from curviest to non-curvy. Okay, so the displacement function would be graph A, and the velocity function would be graph C, and the acceleration function would be graph B. Okay, they didn't ask for this function here. Write down the value of t when the velocity is greatest. Okay, since the velocity function is c, we know that it is greatest here at the vertex of the parabola, and we can see that the time at that point is 3. So we'll say t equals 3. Okay. Page 2. The displacement, s meters, at time t is given by this function here. Okay? Write down the minimum value of S. Okay. Now, this is not something that you can just look at. And the reason why it says write down is because they wanted you to do it with a calculator, but I want you to try it without the calculator. Okay? So, the way you would do this is what you always do, right? If you want to find the minimum or maximum points of the function s, you're going to want to take the first derivative and negative sine 3t, chain rule 3, plus 7.5, right? So that is the first derivative of s. And if we set this equal to 0, then we'll be able to find the stationary points. And one of those stationary points might be the minimum. Okay, so let's solve for t here. So we have 5 times 3, which is 15. We have a negative 15, sine of 3t plus 7.5 equals 0. Let's subtract 7.5 from both sides. So we have negative 15 sine of 3t equals negative 7.5. And then we can multiply both sides by negative 1. And then we can divide both sides by 15. And we'll have sine of 3t equals 1/2. Now we know that the sine of a certain angle is 1/2. Does that sound familiar? You could draw a unit circle, triangle, or whatever way you've memorized when the sine is 1/2. It's, by the way, equal to 30 degrees, or in this case we want to do radian, so it would be pi over 6. Okay, so 3t would be equal to pi over 6. Okay, t is equal to pi divided by 18. Now remember, there's another triangle in the unit circle which also has a sine of 1/2. It would be this angle, which would be 150 degrees, which is equal to 5/6 pi. So 3t would equal to pi over 6 or 5 pi over 6. And so it would be pi over 18 or 5/18 pi. Okay? So these are two possible values of t that are stationary points. We just need to see if they're minimums. Okay? Okay, so one of the ways we could see if it's a minimum is if we take the second derivative. So let's take the second derivative, which is going to be equal to, let's see, the first derivative, let's see, the simplest place. The first derivative is right here, right? So let's take the second derivative of that. We're going to have equals negative 45 cosine of 3t, and then plus the 7.5 would go to 0. So the second derivative, or the acceleration, is equal to negative 45 cosine of 3t. Let's see what the value is in concavity at each of these 2 points, okay? So we're going to draw a sign diagram for velocity, and it's going to look like this. It's going to be pi over 18 here, and it's going to be 5/18 pi here. And then we're going to try to figure out what these values are equal to when we do the second derivative sign diagram. So let's see, we're going to take pi over 18 and we're going to put it into here and see what we get. We'll get negative 45 cosine of 3 pi over 18, which would be pi over 6. Cosine of pi over 6, cosine of 30 degrees, remember, is square root of 3 over 2. That's equal to 0.866, okay, almost 1. Okay, so negative 445 times 0.866. The important thing is it's a negative number, okay? So this is a negative number, okay? What about when we're 5 pi over 18? Okay, that would be negative 45 cosine of 3 times 5 pi over 18, which would be 5 pi over 6. And the cosine of 5 pi over 6 is negative square root of 3 over 2, which is negative 0.866, which is, the important thing is when you multiply those two together, you get a positive number. Okay, so now let's look at these two. So there's two critical points, or there's two stationary points, those two. Which one of these is a local minimum, which one's a local maximum? Well, remember that when you have plus concavity, that means it is a concave up function, and when it's a negative, it's a concave down function. So pi over 18 is a max, and 5/18 pi is a min. So this is our local min. Okay? Now, are we sure that this local min is the global minimum? Well, to find out if it's a global minimum, we kind of have to look at the function. And if you graph this on your calculator, you'll see that this function is kind of like a diagonal line. This part is a diagonal line. And then the cosine function, which is added to it, kind of makes it makes a function which like goes up and down along the diagonal line. Okay? So the 2 points that have any chance of being a minimum are this point and this point. Okay? And this point we just found. That point is 5/18 pi. Okay? The only thing we need to do now is we need to test the first point, which is t equals 0. Okay? So let's test 2 points. One is s is of 0, and the other one is s 5 pi over 18. We're going to compare those 2 points to see which one is actually a minimum. So s of 0, you can see that the first term is going to be 5 times cosine of 0, which is 1. So it's going to be 5. And then the second term is going to be 7.5 times 0, which is just 0, and then plus 10. So we can see that the value of the displacement at t equals 0 is 15. Okay. What about 5 pi over 18, if we put that in? So that would be 5 cosine of 5 pi over 6. And we know that that is equal to approximately 0.866. Square root of 3 over 2. And, oh, it's negative square root of 3 over 2, right? And then 7.5 times 5 pi over 18. And then plus 10. Okay? And then if we look at that, let's see if that is a smaller number than 15. Okay? We're going to have 0.866 times 5, 4.33. We're going to have 5 times pi, 3.14, divided by 18, times 7.5. 6.54. So the first one is going to be negative 4.33. The second term is going to be positive 6.54. And the last term is going to be 10. So I'm going to add all those together. So I'm going to have 10 plus 6.54 minus 4.33. And I get 12.2. Okay. So, yes indeed, this number here is the global minimum, because we just compared it to the S0 point. Okay, and let's see, write down the minimum value. Okay, find the acceleration a at time t. We just did that in the course of finding the concavity. We found the acceleration function, and then finally it says find the value of t when the maximum value of a occurs first. Okay, so look at the function for a. It's a negative cosine function. Okay, remember the cosine function looks like this. Okay, A negative cosine function looks like this. Okay, and then so it asks, when is the first time the maximum occurs? The first time the maximum occurs is here. Remember that the period of the cosine function is 2 pi. Now, what value is this? This would be half of a cycle, which would be pi. So let's see. If you have cosine of 3t, when does 3t equal to pi? That would be when 3t equals pi. So t is equal to pi over 3. Okay? So the maximum value of the acceleration will first occur, and they say first occur because a cosine, cosine continues to cycle like that. So the maximum value occurs over and over again. The maximum value first occurs at t equals pi over 3. So that would be t equals pi over 3. And the first answer was the minimum value of s. Oh, the minimum value of s would be that, 12.2. Okay? And find the acceleration a at time t. That would be this expression here, negative 45 cosine of 3t. Negative 45 cosine of 3t. Okay. Moving on to number 3. A farmer wishes to create a rectangular enclosure of area 135 meters squared as shown below. Okay. The fencing used for side AB costs $7 per meter. And for the other 3 sides, it costs $3 per meter. Okay. So this is kind of an unusual problem because we never had problems before where they had cost of fencing, especially different costs of fencing depending on the side. Okay. Maybe you got like a yard, and the front of the yard you're going to put some expensive wooden fence, and on the sides and on the back you're going to put chain link fence. Okay, so maybe that's why you have different price fence. Okay, as usual for these area problems, you're going to write 2 different equations, and one of them is going to be based on the area, and the other one is going to be based on the perimeter. So normally area, remember, is length times width. Normally the perimeter is length plus width plus width. What's different this time is they didn't tell you that you have a certain amount of fence. They said you're trying to minimize the cost of the fence. So your perimeter is going to be different. It's not going to be a typical perimeter. Your perimeter is going to actually be the cost of the fence. So instead of perimeter, you're going to have a cost equation. Okay? So first we're going to make, we're going to define which side is length and which side is width. Let's say that these 2 are width, so we'll mark them W, and these 2 are length, we'll mark them L. Okay, it doesn't really matter. Alright, so we'll say area equals length times width, that's the area. And in this case, we're not trying to optimize the area or anything because we have the area. The area has to be 135 meters squared. Okay? What about the perimeter equation? Instead of a regular perimeter equation, because we don't have the amount of fence we're going to use, we only have that we're trying to minimize the cost. So we're going to make a cost equation instead of perimeter equation. And so the cost equation is going to be the cost of the green part and the cost of the orange part. Okay? So how do we write the cost of the green part? The cost of the green part is going to be $7 times the width. And the cost of the orange part is going to be $3 times the length plus $3 times the length plus $3 times the W. And then we're going to add all this together. So we're going to have 7W plus 3W is 10W, 3L plus 3L is 6L, and that's equal to the cost. Okay, now, what do we want to optimize? We want to optimize the cost. The cost is minimum. Okay, so we're going to optimize the cost. So we have an equation here, cost equals something something. We need to make it so that cost on the left only has an expression on the right that has 1 variable and not 2. So how do we get rid of one of the variables? We use the fact that length times width multiplied together equals 135. So we could get rid of either length or width. Okay, let's do this. Length equals 135 divided by W, right? Okay, now let's take this expression and we're going to plug it in for L. And then we're going to have C equals 10W plus 6 times 135 over W. And we're trying to optimize the C value here. Okay? So, let's see. Can we multiply this out? We're going to have 10W plus 6 times 135. 6 times 135. Since you don't have a calculator, I'll empathize with you and also do it without the calculator. 18, 21, 6, 7, 8. 810. 810 divided by W. Okay. And so we're trying to optimize this cost. So what's the first thing you're going to do when you're trying to optimize a cost? You're going to take the derivative. So the 10W becomes a 10, and the 810 divided by W becomes a negative 810 divided by W squared. Okay, and then you set it to 0 because you want to optimize it. You're looking for a stationary point. So now you have 810 W squared is equal to 10. W squared is equal to 810 divided by 10, which is equal to 81. W squared is equal to 81, so what is W equal to? 9. Okay? So we have a stationary point, W equals 9, and we want to know if that is indeed a minimum. So the way we could figure out if it's a minimum is we could take a second derivative, but it's probably easier just to make a sign diagram and say, okay, I'm going to make a sign diagram for the cost and the derivative of the cost function. And then I'm just going to plug in. We know that if we put in 9, we're going to get a 0 point. Now, what if we put in something less than 9, like if we put, I don't know, 3 or something. So if we put in 3 in for W, then we'll get 10 minus 810 divided by 3 squared, which is 9. Okay, so it would be 10 minus 810 divided by 9, which would be 10 minus 90, which is a negative 80, which is a negative number. So this would be negative. And then what if we put a number bigger than 9, like, I don't know, 10 or something? So if we put 10 in for W, then we would have 810 divided by 100, which would be 8.1, and 10 minus 8.1 is positive, so we would have positive. Okay? So we can see that the shape of the C function would be negative gradient, stationary point, and positive gradient. So we can see that 9 is indeed a local minimum. Okay? So we verified that 9 is a minimum. So then, now that we know that W is 9, we can also figure out the length, because the length is equal to 135 divided by W. Okay? All right. And, but what they really wanted to know is the cost. And the cost is equal to 10W plus 810 divided by W. And so let's put in 9 for W here and here. So we're going to have 90 plus 90 is equal to 180. So our cost is going to be 180. All right, and that's it.